So formulation-wise, this is how we know. If you consider the linear impulse and linear momentum, they follow this relationship. In other words, when we are dealing with linear velocities, they will lead you to linear impulse, because when you use linear velocity, you use linear impulse, which is this thing here. And linear impulse is depending on force. And if you use the angular form, which means that if you're provided with angular velocity, then everything you know is the moment. So linear velocity relates to force, angular velocity are related to moments, right? So this is just the by definition. However, we also know that linear velocity and angular velocities are related by what? So how are these two related? Linear velocity and angular velocity. They are related by this. We know that linear velocity equals to omega cross r, right? We also know this, which means what? Which means that, in fact, if you know one, you can know the other. You can convert each one of them back and forth. And that's why, even so formulation-wise, it looks like, well, this is moment for angular impulse. In linear impulse, we have force. So it may look different, but if you realize that this B and this omega, they are actually related. Now here, that means the force and moment are also related, which means that the principle of angular impulse and angular momentum is actually not so different from the principle of linear impulse and momentum. They are, in fact, exchangeable. If you know how to convert force to moment, which I trust you know how to do it, and as long as you know how to convert linear velocity to angular velocity. Now, only one thing you have to be very careful is this conversion is also associated with the change of inertia. Linear inertia is always mass, that you know, and angular inertia is mass moment of inertia. Correct? So, first of all, how do you convert force to moment? We can talk about this one by one. This force to moment, as you know, is very simple. What is moment? Moment equals to what?
Force times the distance.
Force cross moment equals to force cross distance, right? You cross force with a distance, or we call it force arm. You get moment. So this relationship, you know, this is not from dynamics. It's actually from statics or strength of material. Correct? So this is from force to moment. Now, what about from mass to mass moment of inertia? How are these two related? They are related by radius of gyration. Remember, what is radius of gyration? We use regular K, right? So I'll just give you the expression here. IG is nothing but just kg times kg squared times m. Right? No, it's the other way around. Kg equal the square root of what? What is kg? So actually, I think that was correct. Ig over m, right? So Ig is kg squared times m. What I did was before it's correct. Right, remember? And the kg here is radius of gyration. So from radius of gyration, mass and mass moment of inertia can actually be related by a linear coefficient. Radius of gyration, that means these two are related. So you know how to convert force to moment from here. You know how to convert mass to mass moment of inertia. right? Now the last one, how do you convert linear velocity to angular velocity? Just like this. From kinematics, which we learned before. Okay. Now, with this quick review, you know that this principle of angular impulse and momentum is not so different from from principle of linear impulse and momentum. It can be easily related. Now let's start with one example. What is example 29? Example 29 regards the problem like this. And suppose we have a garage, and the garage has a door like this. And the door or the ground is defined like this. And there's a vehicle actually hitting the vehicle is something like this. And the vehicle carries an initial velocity, which is vc. At this point, we define as point A. And the point of impact, we call it point C here. And the bottom of this garage door, we call it point B. And dimension-wise, from point C to the ground, this is 0.25 centimeters or 0.25 meters. And the garage door has a height of 2 meters. Okay, so what is the problem? The problem is after the impact, and because point A is a hinge point, which means that the door, once being the pound impact of this vehicle with this initial velocity, the door is going to swing. I know this is not a modern door's design, but the door is going to swing like this. When it swings up, it goes to this position. If we calculate the angular change, which is the original angle to here, this angle is, we call it maximum angle is theta. Theta is 150 degrees, which means once the garage door is hit by this car, it swings up and goes up to 150 degrees, measured from the vertical position. So that's 150 degrees. So what are we trying to determine? We are trying to determine what will be the linear impulse. We want to find out what is a linear impulse. By the linear impulse, which is this. Linear impulse is defined by from T1 to T2, force dt. We want to know what is this term. And of course, you can write it as capital I from 1 to 2. We want to know what is this. Find out the linear impulse of this problem. That's what we want to know. And of course, we are provided with the mass of the door. And the mass of the door is 20 kilograms. We also have the dimension of the door. And we also want to know that what is the linear velocity. And the linear velocity of this door, the linear velocity of the vehicle is what? Well, let's define the problem by understanding what is the force here first. The force is provided by this this point. So this is impact force. So when we want to calculate the linear impulse is actually the force provided by the vehicle at the point of contact. And the center of gravity of this garage door is at the center of geometry, which is somewhere here.